Okay, so let's start with a little thought experiment. Picture this. You're on a road trip. Your destination is exactly 120 miles away, and you manage to get there in precisely 2 hours. Now, this sounds like a simple setup, but it leads to a question with a surprisingly deep answer, one that gets right to the very heart of calculus.
So think about it for a second. Your average speed was 60 miles per hour, easy enough. But you know you weren't driving at one constant speed. Of course not. You were speeding up on the highway, you slowed down for a bit of traffic, your speedometer was all over the place. So, is it an absolute guarantee that at some exact moment your speedometer needle hit 60 on the dot? Or is it possible you are always just a little bit above it or a little bit below it?
You know, what we're really getting at here is the connection between two huge ideas in calculus. On one hand, you've got your average speed for the whole trip. That's what we call the average rate of change. And on the other, you have the speed on your speedometer at any given second, and that's the instantaneous rate of change. The mean value theorem, well, it's the bridge that connects them.
Now, to really understand this main theorem, we're going to start with a simpler case first. It's called Rolle's theorem, and you can think of it as our main idea just applied to a very specific and much flatter kind of trip. So forget about distance for a minute, and let's think about elevation. Imagine you're on a scenic drive through some hills. You start in one town, and you end in another town, and they just happen to be at the exact same elevation above sea level. You go up, you go down, but vertically speaking, you finish right where you started.
Okay, here's the formal definition. It's got 3 conditions. First, the function has to be continuous, which just means your path doesn't have any sudden jumps or teleportations. Second, it's got to be differentiable. No sharp instantaneous turns, just a nice smooth ride. And third, g of a equals g of b. You start and end at the same height. If all that is true, the theorem guarantees there's at least one point c where the derivative is 0.
And that's the whole idea in a nutshell. A derivative of 0 just means a slope of 0, perfectly flat. If you went uphill at all on your trip, you had to eventually come back down to end at the same elevation, right? Well, right at the very peak of that hill or the very bottom of a valley, for just a split second, your path had to be perfectly level. Rolle's theorem is the guarantee that that flat spot exists.
All right, so we know that if you start and end at the same height, you're guaranteed to have a moment where you're perfectly flat. But what about our original road trip, where we start at mile 0 and end at mile 120? Well, that's where the main event comes in, the mean value theorem.
Now notice how similar this sounds to Rolle's theorem. It needs the same kind of smooth ride. The function has to be continuous and differentiable, but here's the kicker. It drops the requirement that you have to start and end at the same spot. This theorem applies to any journey, no matter how steep the overall hill is.
And this is the beautiful equation at the heart of it all. It might look a little abstract at first glance, but it's telling us something incredibly intuitive. This simple formula is the guarantee we were looking for on our road trip.
Let's just break this down. The left side of that equation, that's your end position minus your start position, all divided by the total time. Hey, that's just distance over time. It's your average speed for the whole trip. And the right side, f prime of c, that's the derivative. That's your speed at one specific moment c. It's your instantaneous speed.
So what's the theorem saying? It's saying these two things must be equal at some point. It guarantees that there was at least one moment in time where your instantaneous speed was exactly the same as your average speed. The answer to our opening question is a definite, resounding yes.
Now, there is one really important catch. The ride has to be smooth, or in math terms, differentiable. Think about the function f of x equals the absolute value of x. It makes that sharp V shape with a corner right at 0. At that sharp point, the slope isn't really defined. The average slope from -1 to 1 is 0, sure, but there's no point on that graph that has a perfectly flat tangent line. That's why the smooth ride condition is so important.
Okay, so this is a pretty cool guarantee, but why is this one of the most important theorems in all of calculus? Because it gives us an incredibly powerful tool for analyzing how things change. It helps us find the highest and lowest points of any journey, whether we're talking about elevation, a company's profit, or even the temperature.
So let's go back to our scenic drive for a minute. Imagine you could know your instantaneous rate of change in elevation at any moment. So if that number, your derivative, is positive, what does that tell you? What if it's negative? Well, it turns out the sign of the derivative tells us everything we need to know about the direction we're headed.
This table lays it all out, and it's really straightforward. If your derivative is positive, the function is increasing. You're going uphill. If it's negative, the function is decreasing. You're going downhill.
And if it's 0, well, that's one of those special flat spots we talked about with Rolle's theorem, a potential peak or a valley. This is true for pretty much anything that changes smoothly over time.
This leads to an awesome strategy for finding the absolute highest point on any given interval. Think about it. The highest point has to be in one of 3 places, at the start, at the end, or at one of those flat spots where the derivative is 0. So you just find those few critical points, check their values, compare them, and you're done. You don't have to check every single point in between.
Let's just look at a quick example. We find the flat spots where the derivative is 0, in this case at x equals -1 and 3. Then we check those values against the values at the start and end points. And just by comparing those 4 numbers, we can see the highest and lowest values over the whole journey. Notice how the point at x equals -1 is a local peak with a value of 11, but the true lowest point of the entire ride, the absolute minimum, is actually -151 right at the beginning. It's a super efficient method.
So far, we've been looking at paths that are pretty easy to describe with a y equals f of x kind of formula. But what happens when the path is more complicated? To find the slope on any kind of curve, we sometimes need a more powerful technique.
Take a circle, for example. It's a perfectly simple shape we all know and love, but you can't actually write it as a single y equals function. For any given x value, you've got 2 possible y values. So how in the world do we find the slope on a curve like that?
A circle famously fails the vertical line test, which is that old graphical check to see if something is a function. This means our standard method of taking the derivative just isn't going to work directly on this equation. We need a new tool.
And that tool is called implicit differentiation. And the genius of this technique is that it lets us find the derivative, the slope, without ever having to isolate y on one side of the equation. It just works with the relationship between x and y exactly as it is.
And just look at the result it gives us for our circle. The slope at any point is simply -x divided by y. It's an incredibly simple and elegant formula that perfectly describes the steepness at every single point along the circle's path. How cool is that?
And that brings us right back to our big idea. Whether we're using simple derivatives or more advanced tricks like the one we just saw, the goal is often to understand rates of change. And the mean value theorem gives us a fundamental guarantee about this whole process. It's not just for road trips. Think about the stock market, the temperature outside, the growth of a company. For any of these, you can calculate the average rate of change. And this theorem guarantees that at some moment, the instantaneous rate was exactly that average. So the question to leave you with is, what other hidden guarantees are just waiting to be noticed in the world all around you?